Now, these properties of integrals, we're going to use these two to prove something about the relationship between limits of Riemann sums, definite integrals, and indefinite integrals, or antiderivatives. It's called the fundamental theorem. What we're going to start off with is using this min-max inequality. So here's the idea. Let's just suppose that we have a function that's continuous. So if f is continuous on some interval a, b. If it's continuous, we know that it's integrable, so we could calculate the integral from a to b of f of x dx, and that would be a number. Now we know from the min-max inequality that f dominates its min, and so the min of f times b minus a would have to be less than this integral, while the max of f times b minus a would have to be more than that integral. What I'm going to do is divide both sides by b minus a so that I get the min of f is less than or equal to 1 over b minus a times the integral from a to b of f of x dx, which we recognize as being also the average value, mean value. Okay, and if I divide max b minus a by b minus a, then I have the max of f. Okay, so here's this number. It's a number between min f and max f. The average value of f is somewhere between its min and its max. Well, that makes a lot of sense. Now, if f is continuous, here's a, here's b, and we know at some point f is down here at min f. Maybe this is min f right here. And at some other point, maybe later on, maybe before, f ends up being up here at max f. Then here's a number in between those two. So in between those is the average value. Let's call this guy the average value of f. The average value of f is somewhere between the min and the max. I'm going to draw that. Now if f is continuous, then the only way to get from the min to the max would be to at some point cross through that average value. So we can see there's some point here between a and b, where the value of f at that point actually equals the average value of the function. Okay, so this is called the mean value theorem for definite integrals. It's saying at some point the function actually achieves its average value over some interval. We're going to use that, we said, to prove the fundamental theorem. So the fundamental theorem, we start off by taking our function. So remember we have that f is continuous. Let f be, how about that, continuous on some interval a, b. And we're going to define a new function, capital F. So this is little f. We're going to define a new function, capital F of x. And what we're going to do to define this function is we're going to define it to be a definite integral. That means we're going to define it as a limit of Riemann sums. Let's see, I can't have the variable x here because the variable x, I want to have that up in the upper bound. Okay. Now, if you want to see how capital F works, what capital F is doing is, here's our function little f, and to find the value of capital F, what we're doing is you give me an x, and I'll sum up all the area underneath little f up until I get to x. So that's going to be the value of capital F at x. If you give me a different value for x, like let's say you give me a value that's x plus a bit, then I'm just going to add up more area. So I'll take all that area plus, and that will be f of this other input value. So for any value between a and b where this function is definitely integrable, I could figure out the value of this function, capital F of x. Now the claim is that the derivative of capital F with respect to x is equal to little f of x. In other words, this function capital F that we define is a function whose derivative is little f. So this is a way of constructing an antiderivative. Now let's see if we can actually prove that if you make a function capital F this way, that its derivative will be little f. Remember, by definition, the derivative of f with respect to x would be the limit as h tends to 0 of capital F of x plus h minus capital F at x all over h. We can see that's the limit as h tends to 0 of the integral from a up to x plus h of f of t dt minus integral from a up to x of f of t dt all over h. Now, by our additivity property, if we accumulate all that area, but we remove the area up to this point, then we're just left with the area in between. So this is actually the limit as h tends to 0 of the integral from x to x plus h of little f of t dt all over h. Now if you look at this, this is actually something we could apply the mean value theorem. This is basically the average value of f on this little interval from x to x plus h, because the length of the interval, normally we'd think a to b, right, and then this would be b minus a. But if a is x and b is x plus h, then b minus a is h. So by the mean value theorem, there exists, by the mean value theorem for definite integrals, there exists a c that's between those two values, x and x plus h, such that the integral from x to x plus h of f of t dt all over h is equal to the value of that function f at c. So really, we're talking about the derivative of f with respect to h. It's the limit as h tends to 0 of these values f of c. Now, as h tends to 0, then c gets more and more limited in where it can be. C has to be somewhere between x and x plus h, but as h tends to 0, c is going to get squeezed closer and closer to x. Now, since f is continuous, then the limit is going to be f of x, right? Basically, by making h go to 0, we're actually making c get closer and closer to x, because c is trapped between x and x plus h. So if you let h go to 0, then c gets squeezed to x, and since the function is continuous, as c approaches x, right, the value of the function will approach the value of the function at x. And that's it, right? We've shown that the derivative of f with respect to x is little f. So what that means is, if you have a function that's continuous, you're guaranteed that you can construct an antiderivative of it using limits of Riemann sums. That's what this definite integral is, and we're using that to construct some function of a variable. Okay, so that's our first connection between limits of Riemann sums and antiderivatives. We can use a limit of Riemann sums to create an antiderivative. Let's do an example here. Suppose someone asks us to find the derivative of this function. Well, look, what we have is the integral from some constant value, in this case 0, up to x of some function of t, right, dt, and we're supposed to take the derivative of that with respect to x. By what we've just proven, the derivative of this is the original function little f, so we'll get little f of x.